there will be three main focus, and then of course there's some subtopics. So the first one is about ideal cycles. So I will introduce the ideal cycles of gas turbine engine for power plant and for aircraft. Okay, and the different types of modified cycle. So we have a basic cycle or simple gas turbine cycle, the main component, and some of the modified cycle with extra heat exchanger, reheat, intercooling, etc. Okay, and then we see we'll cover on the methods for accounting component loss. Okay, the factors that affect, okay, the energy loss or the performance loss of the of an aircraft engine, of the cycle. And last one is about the design point performance calculation, some of the equation formula to evaluate the performance of the cycles. Okay, so we start. Okay, next, the learning outcomes. Okay, it's about cycle performance, cycle conditions, and different gas turbine cycle. Okay, first one, the shaft power cycles. So there are a number of possible varieties of gas turbine cycle. Okay, so like I mentioned just now, we have multi-stage compression with different low compression, high compression, okay, expansion with high pressure and low pressure turbine, heat exchange, reheat, intercooling. Okay, so there are numbers of example of gas turbine, the basic one and the modified one with extra heat exchanger. Okay, so of course these cycles have its inefficiency or energy loss, performance loss, okay, of the due to the various components that we will see later on, okay, due to various factors which will result in the performance decrease. Okay, so but there are some of the important parameters that we use in order to characterize this performance. So one of them is specific work output. So we will see this later on. Okay, the specific work output from the cycle and the cycle efficiency. Okay, so these parameters depends basically on the pressure ratio and the maximum cycle temperature. Okay, pressure ratio is normally the ratio of the pressure, of course, inlet, outlet, exit of the compressor. Okay, so at the beginning of the aircraft engine, normally we have a fan, and after that we have a compression process. Okay, compressor. So this ratio of inlet and outlet, okay, of the compressor is one of the main character. Okay, main performance parameters. Okay, to evaluate the performance of this gas turbine cycle. So pressure ratio one, okay, pressure, so sometimes the pressure ratio, sometimes we write it as pi, we use notation pi, okay, like this. So the pressure ratio, we use the number of location or exit and inlet of the compressor, okay, or sometimes we know it as R. Okay, so and then the maximum cycle temperature. Okay, for basic gas turbine cycles, which has the basic, which only needs minimum 4 components, which is the first one is compressor, second one is the combustion chamber, and then turbine. Okay, and for power plant gas turbine closed cycle, we have a condenser. Okay, this is for gas turbine closed cycle. Okay, so maximum cycle temperature is usually the temperature at the inlet of the turbine. Okay, means before the expansion. Okay, so imagine if we have this basic cycle, normally we will describe, okay, the performance of a gas turbine cycle in a diagram, okay, a graph diagram. Usually the diagram, actually there are lots of thermodynamic cycle diagram. Okay, the one that we usually use is the TS diagram. T temperature, of course, and S is entropy. I think I've mentioned a bit about entropy during previous class. Entropy is second law, the second law of thermodynamics. Okay, that accounts for the irreversibility of the process of the cycle. So usually we use this TS diagram to describe, okay, the cycle of a gas turbine engine. So the basic cycle of a gas of the TS diagram of a gas turbine engine is something like this. Okay, so we have compression, combustion chamber, and expansion for open cycle. Okay. Okay, so the maximum cycle temperature is at this one, okay, before expansion. Okay, so sometimes we note it as TIT, turbine inlet temperature. So it is the inlet temperature of the turbine, okay, before expansion process. Okay, so that parameter, okay, maximum cycle temperature also determines the specific work output and the cycle efficiency of a gas turbine cycle. Okay, so those two some of the important parameters for a gas turbine shaft power cycle. Okay. Next, okay, ideal cycles. Okay, usually, okay, before we proceed with evaluation, measurement of the cycle process, okay, a gas turbine cycle, we have to make some assumption first, okay. So normally if you read papers, articles concerning gas turbine cycle or aircraft cycles, right, from journals, so we have to always mention first what are our hypotheses, what are our assumption before we can proceed with the simulation or modeling or calculation, etc. We have to make our assumption first, even though our assumption is far from the ideal or far from the truth, or deviate a little bit from the ideal, from the reality, from the actual process. But we have to state this assumption. Okay, so I just mentioned this because maybe later on, maybe next semester, when you will do your dissertation, I think not just about propulsion, maybe other area as well. Okay, so when you do your dissertation, so because it's about it's kind of like the thesis research. So when you want to propose your topics or your proposal about this topic, you have to mention first what are your assumptions, because this will lead to your application on which equation or which parameters that you want to use. Okay, so if you didn't mention at the beginning, for example, that you consider the cycle is isentropic, for like example the first one here, reversible adiabatic isentropic, so maybe some of the equation of state or some of the parameters that you're going to apply, it is not valid except that if the cycle only reversible adiabatic isentropic, means that the equation may be only valid for this isentropic process example. Okay, so that's why it is important, especially if you are doing research or you are doing evaluating something, right, experiment, it is important to state first, clarify first what are our assumptions. Okay, so these are the most some of the most critical point in our when we want to evaluate something. Okay, so these are the 6 assumptions or hypotheses normally that we clarify first, justify first, before we proceed with ideal conditions process. Okay, so the first one, when we so this is ideal conditions. Okay, ideal means normally the best performance, the best perform that we can expect from a gas turbine cycle, thermodynamic cycle. Okay, so the first one is compression. We assume that the compression and expansion process are reversible and adiabatic, which is also named as isentropic. Okay, if you can recall, what I have mentioned I think the first week. Okay, these are some of the definition in thermodynamics. Okay, just I will repeat again. Okay, inshallah. Okay, so reversible and adiabatic. Okay, this relates with the second law of thermodynamics just now as entropy. Okay, when we say that the process irreversible, means that it has no energy loss. We assume that there's no loss, which is almost impossible, right? In reality, to have nothing lost. Okay, but this is ideal that we assume. Okay, reversible means that the process can be reverse. Okay, macam flashback balik, kan, patah balik, reverse, which is normally it's not true lah. Okay, so like we always have like friction loss, kan, okay, so energy loss. So but in this ideal case, we assume that the compression and expansion, okay, process are reversible and adiabatic. Okay, adiabatic maybe a term that we other than outside thermodynamics, we seldom use this term, right? Reversible maybe we use it. Okay, reverse, not reverse, kan? Okay, adiabatic. Okay, adiabatic means that like no heat transfer between the system or control volume that we choose, or the cycle or the component with outside. We assume that there's no heat transfer. Okay, so if we assume that the system is or the compression expansion is adiabatic, means that the delta Q, this is, I hope that you have seen this notation delta or differential in engineering, the remedial course engineering maths. Okay, or we can also write dq, the differential form. Q is the heat transfer. Okay, heat transfer, the notation for heat transfer lah. Okay, so okay, when we say that the process or the system is adiabatic, means that we assume that the delta Q is 0. Okay, means that there's no heat transfer change, okay, between the system. Okay, if here compressor lah. Okay, compressor, we assume that the between the compressor and the environment outside, there's no heat exchange. So that's why we call that the system, the process is adiabatic throughout the process. Okay, so when the process compression and expansion reversible and adiabatic at the same time, ada dua kriteria ni, both of these criteria are met, reversible and adiabatic, then it is named isentropic. Or I don't know how you pronounce it. Okay, isentropic. Okay, so isentropic is what in second law of thermodynamics. Okay, so you must have these two criteria, reversible and adiabatic. Okay, not only one. Kalau satu je, if only one reversible, then it is not, maybe it is not isentropic. Okay, so this is the first one that we assume for compression and expansion process, mean in the compressor and in the turbine. Okay, next, second one, we assume that the change of KE is kinetic energy. Okay, kinetic energy, KE of the working fluid between inlet and outlet of each component is negligible. Okay, also this is a bit simplicity. Okay, simplified. Okay, but it is ideal condition. Okay, we assume that the change of kinetic energy of the working fluid, inlet and outlet of each component is negligible. Means of each component means within the compressor, combustion chamber, what else just now, turbine. Okay, we assume within those components, okay, those basic components of gas turbine cycle, there's no change of kinetic energy. Means that we assume, for example, compressor, the velocity of the fluid, usually air, okay, air. The working fluid is air. Normally for aircraft engine, right, air, okay, oxygen, etc., right? Okay, so working fluid is the main fluid in the working gas, the main fluid in the gas turbine. Okay, so air here. Okay, so we assume air. For example, just now compressor, inlet and outlet of the compressor, the velocity you assume to be the same. Okay, no change in kinetic energy. When we mention kinetic energy, it must be related with velocity, speed. Okay. Okay, when we mention kinetic energy, mesti cakap pasal velocity lah. So, dia berkaitan dengan velocity. Kalau potential energy, is about the altitude, right? Gravitational force. But kinetic energy is about velocity. So, we assume that the velocity of inlet and outlet of each component, for example, compressor, outlet and inlet of the compressor is, there's no change. Maybe we assume that it is nearly constant, no change, or maybe or very, very small changes. Okay, compared to the velocity at the nozzle, for example, right? Okay, so when the velocity of the inlet and outlet no change or very, very small change, so we can say that this there's no change of kinetic energy. Okay, there's no kinetic energy between the component. Okay, so this is what it meant, the second assumption. Okay, we neglige, it is negligible. So we neglige the kinetic energy within the compressor, we neglige the kinetic energy in the combustion chamber, we neglige the kinetic energy in turbine. Okay, due to the small change of velocity of air, working fluid, outlet and inlet of each of these component. Okay, the third one, there are no pressure loss in the inlet ducting, combustion chamber, heat exchanger, intercoolers, exhaust ducting, etc. Okay, so this if we have okay, the complete cycle. Okay, we have the inlet ducting, the nozzle diffuser, extra heat exchanger, intercooler, etc. We assume that there are no pressure loss. Okay, assumption. Okay, no pressure loss means that, for example, the combustion process, the mixture between the fuel burn with the fuel and the working fluid air, okay, with no pressure loss. Okay, no pressure, which means that the process is in constant pressure isobar. Okay, constant pressure. Another term for constant pressure, we use isobar. The process is isobaric, isobaric process, isobar, constant pressure. Okay, but usually there are somehow there is somehow a pressure loss. Okay, but here for ideal conditions, you assume there are no pressure loss. Okay, so mean that the pressure at for example, for combustion chamber, the pressure exiting the combustion chamber is the same as or nearly the same as the pressure entering the combustion chamber. Okay, so we assume that the P exit combustion chamber equal to P inlet of the combustion chamber, and the same for those other heat exchanger. Okay, okay, so these are the three first assumption, and then the other three. The working fluid has the same composition throughout the cycle and is a perfect gas with constant specific heat. Okay, perfect gas or ideal gas. Okay, the working fluid again, the air. Okay, usually air. Okay, it can be other fluid as well, refrigerant as well. But here, when we are talking about aero engine, aircraft engine, usually it is the working fluid is air. Okay. Composition throughout the cycle is perfect. Okay, so we assume that the air, the working fluid is perfect gas or ideal gas. Okay, okay. When we mention when we assume that it is ideal gas, means that we can apply the ideal gas property to the working fluid, to the air. Okay, so one of the important parameter for ideal gas is this one. PV equals to NRT. I want to, okay, I use this one. Okay, but because there are some different ratio, but I will use this one. PV small v equals to RT. Okay, so P pressure, V, the small v is a specific volume, means in meter cube per kilogram. R is gas constant in joule per kilogram per Kelvin, and then T temperature lah. Okay, so R is a gas constant. So it is always given. I mean, we can search for the value. It is a fixed value. So R, for example, for air, is 287. This one is in joule. Joule per kilogram per Kelvin. Okay. So for different gas or different fluid, different value of R. So this R gas constant depends on the types of fluid. Okay. Yes. So this is one of the characterization, character of the ideal gas or perfect gas. Okay, with constant specific heats. Okay, wait before so when we say that ideal it is ideal gas, we assume that the working fluid air is ideal gas, so we can use this. One of them is that we can use this ideal gas equation of state. Okay. uh, this is important because it relates for example, the pressure with temperature. So if we know the pressure, we can search for temperature. If we know the temperature, we can search for the specific volume, for example, right? So this equation is important, but we can only apply this if we assume the working fluid is ideal gas. So that's why it is important to make this assumption. Okay, constant specific heat. Constant specific heat, this one. Okay, this specific heat, it has the same unit as R, gas constant. Usually it is noted as CP. Okay, C with a small p at the end there. Okay, CP. This CP is what we call specific heats. Okay, specific heat at constant pressure, P constant pressure, because there's also CV, okay, with small v, means specific heat at constant volume. Okay, so but here usually we use CP for aircraft engine, aero engine, gas turbine cycle. Okay, so specific heat is also in joule per kilogram per Kelvin. For air, usually it is around 1005 or 1.005 kilojoule per kilogram per Kelvin. Okay, 1.005 kilojoule per kilogram per Kelvin. Okay, you don't have to memorize this value, but when you always we do the calculation, one day you will remember that. Okay, so CP is 1.005 for air. Okay, so what is CP? CP is the specific heat, means the amount of energy needed in order to heat, or because it to heat to increase the temperature of 1 Kelvin or 1 degree Celsius, for each mass of the fluid of the substance. Okay, here is the air. Okay, so that is specific heat. Okay, but for this ideal cycles, we assume that the specific heat is constant. Okay, but however, I just want to share with you, actually in these specific heats, it depends, it varies depending on the temperature. So sometimes if you read if you saw other equation, something like this, CP function of T temperature, and there's different correlation, different equation for CP, which varies depending on the temperature. Okay, so in the real situation, this specific heat varies with temperature. Okay, but for ideal case, you assume that it has a constant value, so we can just take the value given. For example, here for air is 1.005. Okay. Next, number 5, the mass flow of gas is constant throughout the cycle. Okay, this is from the conservation of mass. Okay, conservation of mass. Remember that there are three law of conservation. The first one is conservation of mass. Second one is conservation of momentum, which is the Newton's second law. Newton's second law. So that is where we get the thrust equation. Newton's second law, the sum of the force equals to ma, F equals to ma. Okay, so that is derived from conservation of momentum. And the third one is conservation of energy, which is the first law of thermodynamics that we were talking about. Okay, so the first one is conservation of mass. Okay, conservation of mass means that the mass flow rate and the mass flow of the gas is constant throughout the cycle, does not change. Okay. This is assumption. Of course, actually the mass flow of the gas will be changed, will be modified, because it's one of the reason we will add fuel. Okay, fuel to the working to burn mixture of the in the combustion process. Okay, but here we assume that the mass flow is constant due to the mass of the the mass of the fuel added is very, very small. Usually the mass of the fuel, mass flow rate of the fuel, mf dot, mass flow rate of the fuel mass flow rate, is very small compared to the mass flow rate of the total air working fluid, air intake. Okay, it's not that the fuel there's no fuel, it's not that the fuel is zero or what, but it is very small. That means negligible compared to ma, the mass flow rate of air working fluid. Okay, so that's why we can assume that the mass flow of gas is constant throughout the cycle, gas turbine cycle tadi yang pusing daripada compressor turbine semua tu. Okay, last one, number 6, heat transfer in a heat exchanger. Assume counterflow is complete. So that in conjunction with 4 and 5, the temperature rise on the cold side is the maximum possible and exactly equal to the temperature drop on the hot side. Okay. Okay, so this one, okay, heat exchanger. Okay, for aircraft, for aero engine, we have the basic, okay, the basic aircraft engine cycle just now. We have combustion compressor, combustion chamber, and turbine. Okay, but if we have a modified cycle, gas turbine cycle with extra heat exchanger, for example, intercooling or reheating. Okay, so we have extra heat exchanger here. So that's why we have to assume this number 6. Okay, means that we assume that all of the temperature receive heat. Okay, the function of the heat exchanger is to transfer the heat from between two fluid. Okay, at least we have two fluid in a heat exchanger. Okay, so the function of a heat exchanger is to exchange fluid from the hot, of course, to the cold fluid. Okay, so from hot is always the heat source. Okay, hot from the heat source to the cold fluid. So for example, if in a evaporation, so we have a heat source. If the heat source comes from solar or comes from the burning of the fuel, okay, so that is the heat source, and the working fluid inside the evaporator, the water or the air, is the cold fluid here in this case. Okay, so the heat will be transferred from the hot fluid in heat source to the cold fluid. So we assume that what he's saying in this this assumption number 6, that the whole the total of the heat from the hot fluid is transferred to the cold, means that the heat transfer process is 100% efficient, something like that. Okay, means that the efficiency of the heat transfer is 100%. Okay, so ideal case, normally there's always drop in the heat exchange process. So the heat transfer we have efficiency maybe like we write 0.7 or 0.6, 0.8. Okay, but here in the ideal case we assume that the efficiency, okay, of the heat transfer process in the heat exchanger is 1. Okay, 100%. Okay, So those are the six assumptions that normally we have to mention when we apply this ideal cycle case. Section 4.5 imply that the combustion chamber in which fuel is introduced and burned is considered as being replaced by a heater with an external heat source. Okay, this one if we have if we use um, uh, closed cycle for gas turbine cycle for power plant. Okay, we replace the combustion chamber with a heater or evaporator boiler. Okay, as far as the calculation of performance is concerned, it makes no difference whether it is open or closed cycle. So the formula, all these assumptions that I mentioned just now, can be applied for both open or closed cycle of gas turbine cycle. Okay, I repeat again, one of the different between open and closed cycle for the basic cycle. Okay, so for closed cycle, okay, if you have TS diagram, closed cycle, the basic one, we have something like this, okay. So the first one is compressor, 1 to 2 compressor, 2 to 3 evaporator or boiler, 3 to 4 is the expansion turbine, and 4 to 1 is the condensation. Okay, this is a closed cycle, closed turbine cycle. Okay, another one, if we have TS, open cycle, for example, for aero engine, okay, the cycle is open. Okay, the basic, so we dot here. Okay, so 1 to 2, again, compressor, and 2 to 3 is the combustion chamber. Okay, 3 to 4 is the turbine expansion. Okay, turbine. And then the heat will be rejected to the heat sink outside environment. Okay. So that is but those assumptions can be applied for both open and closed cycles. Okay. Next. So this is the schematic diagram of a simple gas turbine cycle. Okay, so the cycle, it has a name. Okay, so the name is Joule or Brighton cycle. Okay, usually we will use this Brighton cycle name. Okay, Brighton. We will use Brighton cycle. The name Brighton cycle for gas turbine cycle. Okay. So 1 to 2 compressor, 2 to 3 is the heat source added, okay, in the combustion chamber or in evaporator, heat exchanger. And then 3 to 4 is the turbine, okay, expansion. Okay. Okay for the time being? Semua okay ke sampai sini? Okay, Brian? Okay. Okay, okay. Okay, next. The relevant steady flow energy equation. Okay. Okay. So okay. When I start, the first law of thermodynamics. Okay. So we have this energy balance equation, or energy equation. So we can apply this energy equation to each of the component of the gas turbine cycle just now. For example, compressor, combustion chamber, turbine, etc. Okay. So this is the general form of the equation. Okay. Q is the heat. Okay, Q is the heat just now. H is the enthalpy. Okay, enthalpy is in joule, joule per kilogram. Okay, so it is the amount of energy. Okay, joule. And then C here is actually okay. This term, the second term, is kinetic energy. Okay, so sometimes we use V, velocity, or sometimes we use C. So it's okay, either one, either or. So kinetic energy, the second term is kinetic energy, and the third one is work transfer, work done by the component, usually by compressor and turbine, that there are work done those component. Okay, so we can apply this steady flow energy equation, okay, to each of the component. Compressor, for example, 1 to 2 is the compressor, from state 1 to state 2 compressor. Okay, so in the compressor, okay, with the six assumption that we made just now for ideal cycle. So for compressor, the first one from 1 to 2. 1 to 2 here is for compressor. Okay. So compressor 1 to 2, there are no heat transfer. Okay. We assume for ideal case, for a compressor, there are no heat transfer in the compressor, inlet and outlet of the compressor. So that's why there's no Q, there's no heat transfer. But there are work done by the compressor. Okay. Work input by the compressor, because compressor it needs a work, electric pump, to pump. Okay, so it needs energy work. Okay. And then enthalpy H2 minus H1, which is equal to Cp T2 minus T1. Okay, this is the definition of enthalpy. Enthalpy is TH, the differential of enthalpy. Cp just now specific heat. DT. Okay, the difference of temperature. So that's why the assumption that we made earlier is important, because if we didn't mention that for example that the working fluid is the working fluid inside the gas turbine cycle is perfect gas, ideal gas, we could not maybe we could not use this equation, okay, that DH equals to CPDT. Okay, and then the DCP, okay, constant specific heat. Okay, we have defined in the assumption just now that we assume CP specific heat is constant. So otherwise, if we did not mention that, then DCP will have to have we have to include the correlation, the equation for the CP. The CP will not be a constant value. Okay, and then second one, the 2 to 3 is the combustion chamber, the process in the combustion chamber or evaporator. Okay, so for in the combustion chamber or evaporator, there are no work transfer, no work done. Okay, there are only heat transfer within inlet and outlet of the combustion chamber or the evaporator, of course, because we transfer the heat from the hot fluid heat source to the cold fluid, which is the working fluid inside the gas turbine cycle. Okay, so that's why there is heat transfer. Okay, and H again, DH equals to Cp dt, the difference of the temperature inlet and outlet of the combustion chamber or evaporator. And the third one is turbine. Okay, 3 to 4. Turbine. Okay, okay, work transfer. So in turbine is the same as opposite of the compressor. Okay, so there are work being produced, power produced. Okay, power being produced, work produced. But there is no heat transfer. Okay, we assume no heat transfer in the turbine like the compressor just now. So only have work and enthalpy Cp delta T, difference of temperature. So that's how we calculate each of the energy balance. Okay, the performance of each of this component. Okay, compressor, combustion chamber, and the turbine. Okay, and then so why we need to evaluate the performance of each of the energy balance of each of the component just now? Because one of them is the reason is that we want to of course measure the whole cycle, the gas turbine cycle, the whole cycle efficiency, the performance. Okay, so one of the criteria to evaluate the performance of a gas turbine cycle is the cycle efficiency. Okay, so what the cycle efficiency said, it is the ratio of the net work output over the heat supply. this is the general definition of a cycle efficiency. Okay, general definition, work output, what we produce over what we give as an input. Of course, the efficiency will not be 100%, right? Or one, right? Usually the net work output or the power that we produce is less than what we supply, what is being supplied from the heat source, from the source. Okay. So these are the how we calculate the cycle efficiency, the performance. Okay. So work output, since for the basic cycle just now, basic cycle with the only 3 components or 4 components for closed cycle, the work done only in with the ideal cycle assumption, the work done is only within the turbine and compressor, ideal cycle, okay? Ideal and simple gas turbine cycle. The work done only in turbine and compressor. So that's why we only have these 2 terms. This is from the turbine and this is from the compressor just now. Okay. So the energy balance, the energy from the turbine and the energy from the compressor. Okay, which is work here. There's no heat for turbine and compressor, only work. So the work produced by the turbine is usually being used in the compressor, okay, to pump to compress the working fluid air inside within the compressor, right? Okay, so the net work output is work produced by the turbine minus the work input used by the compressor. Okay, and then heat supply. Heat supply is the heat transfer, the total heat transfer at the combustion chamber or at the evaporator. Okay, so this is the heat supply. The Q just now, delta Q just now is equal to Cp, the difference of the temperature inlet and outlet of the combustion chamber or of the heat exchanger. For closed cycle, we need to add another one, Cp minus the T4 minus T1. Okay, in the condenser. Kalau kita ada condenser lah. Kalau kita ada condenser, kita nak add kat sini. Okay, but for normally for aero engines, the simple gas turbine cycle is only this, okay? The heat supply is within the combustion chamber or evaporator, and the work output, power produced is within turbine compressor. So that's how we calculate the cycle, simple gas turbine cycle efficiency. Okay. Another one, making use of the isentropic PT relation we have. Okay. So we want to link this temperature, because we know the temperature at each point of the component cycle.
Sorry.
Yeah.
Yeah, this CP specific heat is a common term. You cannot take it out. It's different for different heat.
Okay. So in this equation, if the CP is the same and constant, actually we can eliminate, right?
Yes.
What you mean? Okay. Yeah. So it's true. Yeah. So if CP, if the same, we assume only air. Okay, ideal because only air and Cp is constant the same, so we can just take out, eliminate the Cp. Okay, thank you. Okay, since we know we measure the temperature at each point of the component, inlet outlet of each of the component, so we can link this. We can use this temperature to calculate also the pressure ratio. Okay, so one of the important parameter for gas turbine cycle is the pressure ratio. Okay, so pressure ratio is noted as R or sometimes pi, pi tu R. Okay, so this is the, okay, this is also from ideal gas assumption. So we can only apply this, that T2 over T1 equals to R, for example, P2 over P1, power of gamma minus 1 over gamma. Okay, this relation, I rewrite it in this way. Saya tulis balik dalam bentuk macam ni. Okay. Okay, so this equation is actually can be applied if you assume that the fluid is ideal gas. Okay, so that's why it's very important to assume ideal gas first. So we can use this equation, this term. Okay, so what is gamma? Gamma is specific heat ratio. So, ada banyak definition. Okay, gamma or sometimes noted as K, small k, is a specific heat ratio. Okay, tak apa, benda-benda yang macam ni boleh tak perlu apa-apa kan, value-value ni, just tahu je. Okay, specific heat ratio, it has no unit. It has no unit, that dimensionless lah. Okay, dimension. This gamma normally for ideal gas, for air, we assume it to the value is 1.4 or sometimes 1.33. Okay, so around that 1.3, 1.2, 1.4. Okay. So gamma, a fixed value, a constant value. Okay, so we can use this relation link between temperature and pressure. So if we, for example, if you know temperature, then we calculate pressure. We can calculate the pressure. If you know the pressure, then we can calculate the temperature. So that's how also we calculate the pressure ratio. Okay, so pressure ratio is this one. Pressure ratio P2 over P1 means the pressure at the exit of the compressor over the pressure inlet compressor. P1 is inlet compressor, equals to P3. P3 is inlet turbine and P4 is outlet turbine. Okay, again, the cycle. 1, 2, 3 atas sebelah 4. Okay, so 1, 2 is a inlet outlet compressor, 3, 4 is inlet outlet turbine. Okay, so that is what we call pressure ratio, or R, or sometimes written as pi. Okay, so the cycle efficiency just now, okay, the symbol eta, okay, can be also written as this way. Okay, the in the red box. Actually, we can just modify. It is derived from this one as well. Okay, we just develop the equation, reposition the temperature, factorize, etc., and then we get this. Okay, you can try, but I think it's not important for me to show those mathematical steps. I just give you the efficiency here. So means that if we don't have access, okay, if we don't know the temperature of each of the component in the outlet of the component, but we have the access to, we know the pressure ratio of the component, means P2 over P1 or P3 over P1, then we can also calculate, measure evaluate the cycle efficiency without knowing the temperature. Okay, so means that we can use either one of the equation lah. Okay, so with pressure ratio also we can calculate cycle efficiency. Okay, next. Lagi 5 minit. Okay, so the efficiency, of course, by from this derivation, from this equation, okay, equation 2.1. So we can see here that the cycle efficiency, the gas turbine efficiency, depends on the pressure ratio. Okay, so means that if we change the pressure ratio, the pressure ratio change, so the cycle efficiency might be changed. Okay, so the efficiency does depends on the pressure ratio and the nature of the gas. So so we can sketch, illustrate we can simulate the change of the pressure ratio with the efficiency. So we can from here from the equation just now 2.1. So we sketch, illustrate this figure, this graphic, efficiency versus the pressure ratio, efficiency of a simple cycle. Okay, so we can see the relation between pressure ratio and the efficiency, the cycle performance. Okay, so for example, if gamma, so that's why gamma for different fluid, different value of gamma. Usually for air is 1.4, for argon, 1.66. Okay, so around 1 point something normally. Okay, so means that by looking at the figure, this figure from the equation just now, we simulate, means that if we increase for this simple cycle, if we increase the pressure ratio, then efficiency will be increased. One of the reason, okay? One of the factor. Okay, yeah, pressure ratio increase, efficiency increase. Okay. So that is one. And then specific work output. Okay. Also is a function of pressure ratio and maximum cycle temperature. Okay. Okay, work output, the net work output just now, this network output, okay, network output, turbine minus the compressor, okay, so turbine minus the compressor, okay, turbine di sana, ni turbine, this is compressor, from the energy balance from the compressor, okay, so this specific work output is depends on the pressure ratio, and also it depends on the maximum cycle temperature, T3, this one. Okay, or we write it as turbine inlet temperature, TIT, the maximum temperature of the cycle for simple cycle. Okay, so this specific work output can also be defined this way. Okay, so from equation 2.2 here, we can see the relation between the specific work output and the pressure ratio. It means actually we rewrite, we modify this first equation, we rewrite it, develop, factorize, etc., and we can produce this second equation 2.2, to link the work output with the pressure ratio R, and also with the what we call here the ratio of the T3 over T1 T. Okay, T3 over T, small t is T3 over T1, not time. Okay, T3 over temperature of the inlet turbine over the temperature of the inlet compressor, which is normally T1 is the atmospheric pressure, atmospheric temperature, T ambient. Okay, T1 is the ambient. So actually T is the TIT, the maximum temperature of the turbine, the maximum temperature of the cycle over T ambient, something like that. So we can see here the relation between the specific work output with the pressure ratio and also with the temperature. Okay, why do we have to express a lot of different equation? Is that so that we can later on we can for example, we can simulate, we can what we can expect if we change those parameter, if we change maximum temperature, so does specific work output will change or not? So that's why if we have this relation, then we can predict, okay, the performance. Okay, so saya dah azan. Okay, I think I will stop here. Okay, 7:30 kot. Okay, we take a break first. Boleh ya?
Okay, doktor.
Okay, we will resume back our class. Everyone is here? Are you guys here?
Yes,
Yeah.
Doctor.
Yes, sir.
Okay. Okay. Okay, so we continue. Okay, share slides, share screen. Podcast. Okay, so three files. So we were at this, I think, this slide just now. Okay, so I was explaining about the relationship. Okay, the link between cycle efficiency and the pressure ratio. Okay, so this figure 2.2, we can is being illustrated sketched by from this equation. Okay, from this equation of efficiency that link the efficiency with the pressure ratio. Okay. Oh, I think we have passed this one, and then specific work also. Okay, specific work output, we have done this also. So this one, okay, figure 2.2b, the relation between the specific work output and the pressure ratio. Okay, so means that for a certain specific amount of the ratio of T3/T1 just now, the maximum temperature to ambient temperature, inlet of compressor. So at a certain value of T2, 3, 4, or 5, we have this relation, okay, this graphic in figure 2.2b here, between the pressure ratio and the specific work output. So means that it has from the figure here 2.2b, we can see that what we can analyze from this figure, for a low T, means 2, mean a low T, small t, a low ratio of temperature T, we have kind of like an optimum peak value of specific work output, depending on the pressure ratio. Means for a low T, ratio of temperature, there is a maximum or a peak value of specific output for a certain value of pressure ratio. Means that if we increase the pressure ratio, then the work output will start to decrease, right? We see. But however, for a higher value of ratio of the temperature, example T4, T5, etc., we can see an increasing, okay, increasing. There's no more an peak value or maximum value of the work output, but we can see that the work can be increased, okay, according to the pressure ratio. So means that at a higher value of T, small t, we can if we keep increasing the pressure ratio, the work output will just keep increasing, but until a certain stagnation value. Okay. Okay, that is the relation between specific work output. Okay, specific work output and pressure ratio. So work output is like the power done, power produced. Okay, the network produced. And then what is the value of T3, and hence the T depends on the maximum temperature, which the highly stressed parts of the turbine can stand for the required working life. Okay, so the T3 just now, or the maximum temperature, okay, means that the this ratio depends on the maximum temperature. Okay, but this maximum temperature, however, is very crucial. I mean, for a turbine, because it still has a certain maximum value that the turbine blade can withstand. Okay, the maximum temperature. It is often called the metallurgical limit. Okay, so the turbine always has a maximum limit temperature that it can withstand. It can handle. Okay, early gas turbine values of T between 3.5 to 4, but introduction of air-cooled turbine blades can allow T to be raised to between 5 to 6. Okay, so maybe we can, through the research, through R&D, okay, we can increase a bit this ratio, this turbine maximum temperature to 5 or 6, okay, so that we can increase, hence we can increase the net work output just now, the power output and the cycle efficiency. Okay. This one is the relation between the work also, the work output and the pressure ratio. Okay, I think I'll pass this one, tak apa. Okay, okay, heat exchange cycle. Okay, so just now all those figures, equation that I show just now, it's about a simple basic gas turbine cycle which only have 3 or 4 components. Now we are going to see what if we add some extra heat exchanger, extra component to the basic gas turbine cycle. Means that we modify the engine. Okay. So the first one is that we add a heat exchanger between the before the combustion chamber. Okay, after the compressor. After two, sorry. So this type of heat exchanger, sometimes we also call it as a regenerator. Okay, this type of heat exchangers. Okay, because heat exchanger actually is a common general term. Okay, so and then it depends on the function of the heat exchanger. If the heat exchanger is the function is to vaporize the working fluid, then the heat exchanger will be called evaporator. If the heat exchanger, the function is the objective is to condense, so it is a condenser. Okay, so here the function of this heat exchanger is to regenerate, to reuse the heat from the hot temperature and transfer it to the cold side of the cycle. So that's why this heat exchanger, we call it also as regenerator. We regenerate the heat in the fluid. Okay, or sometimes we also use the term preheater. This one, preheater, because we preheat the working fluid before we preheat here from 2 to 5. Okay, we preheat the working fluid, the air, before it enters in the combustion chamber. Okay, so sometimes you call a preheater or regenerator. Okay, so when we add extra component, when we modify the cycle, thus the cycle efficiency will be modified also. So if you look at here, the cycle efficiency, the equation will be changed. Okay, actually the temperature change. Okay, from the basics equation just now. Okay, I'll explain a bit the function of this regenerator. Okay, why first we introduce this regenerator. One of the reason is that we want to reduce the use of heat supply, heat source. Okay, if you remember just now, the definition of cycle efficiency is the net work output produced over the heat supply. The heat supply in a aero engine is the heat transfer within the combustion chamber. Okay, the combustion process, the heat transfer within that. So that is the heat supply, basically the fuel that we have to supply. Of course, we want to reduce this utilization of fuel as much as possible, right? Okay, so that we use extra heat. Extra heat is needed. So when extra heat is needed, one of the benefit is that the cycle efficiency will be improved. Mathematically, theoretically, from the equation of the cycle efficiency, we can see that because the heat supply is at the denominator. Okay, bawah tu kita panggil denominator. So then if the denominator decrease, then this efficiency will increase. That is mathematics theoretically. But in terms of the phenomenon, physically, apa yang berlaku adalah if we reduce the use of fuel, reduce the heat source, heat supply to the cycle, to the engine, hence we increase the performance of the whole cycle efficiency. Okay, so that is one of the interest why we add this regenerator, okay, to reduce the heat supply. Okay, so in other way, you can see from the this TS diagram, temperature versus entropy diagram. So that's why this TS diagram is important also for us as an engineer. If you want to design, okay, the gas turbine cycle, this diagram, this graphic figure is important because we can predict, we can simulate how the process is going to work. Right? Okay. So here, basically if for the basic cycle just now, the previous the basic cycle, 2 to 3 is where the heat is being supplied, right? Heat supply, kan? Heat source kan, combustion chamber kat situ kan? 2 to 3. Okay, imagine that we don't have the regenerator yet. Okay, 2 to 3 is the heat supply. So if you look at the cycle efficiency just now, heat supply bawah tu, just now Q is equal to delta Q is equals to CP delta T kan, the change of the temperature at the outlet minus the inlet of the difference of the temperature outlet and inlet of the combustion chamber, 3 to 2, T3 minus T2, right? T2, right? Okay, so if we if the difference of the temperature T3 and T2 is smaller, okay, minimized, is being minimized, thus the heat supply, heat needed, Q will be smaller, minimized also, right? Will decrease also, right? Okay, so that's why thus the fuel needed will be minimized. Okay, so that's why we add a regenerator. So this regenerator will cover somehow the work, the heat that need to be transferred in the combustion chamber. Okay, so it can preheat the working fluid air from 2.5, from temperature 2 to temperature 5. Okay, so it's like we save somehow we save the heat needed to be supplied. Okay, so before with the basic cycle, we need to supply heat to increase the temperature from T2 to T3. Of course, if the difference of the temperature is higher, bigger, of course more heat is needed. But if the difference of the temperature is smaller, so less heat is needed, right? Okay, so that's why if we use this regenerator, the heat supply, this Q, instead of T3 minus T2 just now, the difference of temperature only between T3 to T5. Okay, for this regenerator, T3 to T3 minus T5. Okay, so when the difference is smaller, so the Q supply is supposedly smaller, lower. Okay, fuel needed is lower, minimize the fuel needed. Okay, but how? Okay, but we still need to heat up the working fluid from temperature 2 to temperature 5 at a certain value. Okay, so how we do it? With this regenerator, the concept is we reuse the heat from the hot side of the fluid and use it to regenerate. Okay, regenerate and use it for the cold side. Here, this location is and maybe until 6 is considered as the hot side of the cycle. Okay, 3 to 4 or until 6, the hot side of the cycle. And the 1 to 5, okay, 1 to 2 and until 5 is we consider it as the cold side of the cycle, test turbine cycle, okay? So we use the extra heat from the hot side, okay, after the expansion at number 4, location 4, we use this extra heat to preheat, okay, the fluid at point 2. So this total heat at point 4 will be used to preheat the fluid, the working fluid from exiting the compressor. 1 to 2 is compressor, right? So exiting the compressor, the heat from the hot side will be used to will be generated and used to preheat the working fluid, the air from 2 to 5 at the cold side. Okay, so that is the function. Okay, so kind of we reduce the need of using a higher amount of fuel, okay, heat source. With ideal heat exchange, T5 equals to T4, and I'm substituting the isentropic PT relation, the expression reduced to, okay. So in ideal case, ideal heat exchanger, like I mentioned just now, means that we assume this regenerator, this heat exchanger is 100% efficiency, okay, in ideal case. Means that all of the heat from the hot side will be used to preheat the fluid to the cold side. We assume all of the heat, okay, which is only in ideal case. Okay, so if this ideal case is assumed, okay, then the temperature of T5 at location T4 and T5 will be the same, okay, because we assume 100% efficiency of this regenerator, heat exchanger. Otherwise, if the heat exchanger regenerator is not at 100% efficiency, so the T4 and T5 will not be at the same position, the same temperature. T5 maybe will be less than T4. Okay, so yeah, if the efficiency is not 100%. Okay, but this is ideal, so we assume T4 equals to T5. So the cycle efficiency here will be changed, will become the above one is still the same, because the network output is still the same. Turbine, the work produced by the turbine minus the work used in the compressor, T2 minus T1 over T3 over minus T5 is the heat supply Q. Okay, so instead of T3 minus T2, from T3 to T2, so T3 to only T5. So we reduce the heat supply, we reduce the fuel, supposedly. Okay, we expect to reduce the fuel by adding the regenerator. Of course, there are pros and cons, of course. So that's why research, we always do research. So, and that's why also I ask you to do some literature review, okay, on the different cycle exist. Okay, so what are the pros and cons of this the different method? Okay, so there's always pro and cons lah, bukan semua perfect lah kan. Okay, of course one of the thing maybe bila kita add when we add regenerator, of course we add weight, we add cost kan. So ada pro and cons dia lah kan. Okay, next okay, still on this regenerator cycle. So we can also write the same as just now, the simple cycle. So we can also link the efficiency with the R, pressure ratio, and T, the ratio of the temperature. Okay, so again it's the same thing. We can derive this equation, and from this equation we can sketch this, simulate this graphic, okay, to see the performance of the cycle efficiency according to the pressure ratio. Okay. Okay, according to the pressure ratio. Okay, so means here, okay, from this figure 2.4, we can see here, if we at a certain value, a specific value of T, ratio of temperature, if we increase the pressure ratio with this heat exchanger cycle, somehow the efficiency will decrease. So terbalik opposite daripada yang tadi tu, yang simple cycle tu, if we increase the pressure ratio, the efficiency increase. But for this one, with the regenerator, if we increase the pressure ratio, the efficiency will start to decrease. So at a certain point. So those are the relation and the parameter that affects the performance of the cycle. So depends on our objective, what we want to do. If we intend to increase the efficiency, then maybe we will choose to lower the pressure ratio, for example. Okay, so those are the relations of the efficiency with the pressure ratio. Okay, actually we can sketch this simulate this graphic by using you have learned computer programming kan, MATLAB or even Excel pun. Excel, if we have all the values, so we can generate the data. We generate the data using Excel, and then we just sketch the figure, so we can predict the performance of the engine. Okay. Okay. Again, sekejap sebelum saya tengok sekejap. Specific work output, we don't have the equation of specific work output here, but it just explain here. The specific work output is unchanged by the addition of the heat exchanger, and the curve of figure 2.2b just now, the specific work output versus pressure ratio are still applicable. Okay, so means that for this modified cycle with regenerator, the efficiency change with the pressure ratio, but the work output remain. The trend. Okay, the trend of the work output is the same as the basic cycle just now. Okay. Okay, so this is to get improvement efficiency. So samalah, kita boleh tengok daripada figure tu. Okay, next, the third cycle or the second modified cycle is reheat. Okay, reheat cycle. Okay, so dah tiga daripada simple, and then regenerator, and this one is reheat cycle. Okay, a reheat cycle, a substantial increase in specific work output can be obtained by splitting the expansion and reheating the gas between the high pressure and low pressure turbine. Okay. So we modify the cycle and you apply this reheat method. One of the reason is that we want to increase the specific work output. If we increase the specific output, means that we increase the power output lah. Power output produce increase. Okay, so depends on our objective, our aim. So if you want to increase specific work, does increase the power output, one of the method that we can use is to reheat the cycle, reheat the working fluid lah, by using the reheat cycle. Okay, so how this reheat process is done is that by splitting the expansion and reheating the gas between the high pressure and low pressure turbines. So the turbine, instead of having only one stage of expansion turbine, so instead we have maybe two. The turbine, the expansion process is splitted into two. So a low pressure turbine and then high pressure turbine, or sometimes it has also medium, 3 stage. Okay, so we just look at the 2 stage, low pressure and high pressure turbine. Okay, so we start with high pressure first. Okay, so the high pressure turbine, low pressure, high pressure, okay, the high pressure turbine, 3 to 4. Okay, so the expansion in the high pressure turbine from 3 to 4, and then the working fluid is being reheated, reheat back. Okay, heat sekali lagi in a afterburner, for example. Sometimes the turbojet we have afterburner, or turbofan also we have afterburner sometimes. Okay, so means that the fuel is being burned one more time, okay, once again, reheating the gas 4 to 5, and then expand it again 5 to 6 in the high pressure turbine. Okay, so so the expansion is being done, is being split into twice, okay, 2 times. Okay, so this is what we call reheat cycle. We reheat back 4 to 5, reheat another one more time, the working fluid, okay, the air inside the engine, the cycle. Okay, thus from this approach, this method, we can increase the specific work output because the work done by the turbine is like twice, 2 times, okay, instead of only once in a simple gas turbine. Okay, so this is a reheat cycle. So the turbine work is increased is obvious. The vertical distance between any pair of constant pressure lines increase as the entropy increase. Okay. Okay, so what does it mean by the second point, vertical distance? Vertical distance is the for example 3 to 4 and 5 to 6, the vertical distance of constant pressure. Okay, this is constant pressure line. Yeah, sorry, I forgot to mention. This is the isobar line or constant pressure. Isobar or constant pressure. Okay, so in a TS diagram, we have those isobar line. Okay, so if we assume just now, our assumption, one of our assumption is to assume that no pressure loss. Okay, so no pressure loss means isobar, the process is isobar. So the pressure between 4 to 5, for example, or 2 to 3 just now in the combustion chamber is the same, no pressure loss. Okay, so that's why the figure, okay, if we illustrate the sketch, the diagram, the process is along the isobar line, along the constant pressure lines, 4 to 5, 2 to 3, okay, of constant pressure lines increase as the entropy increase. Okay, okay, so means that if we entropy is the S1, means that at this point, this is I call it SA, and this is the this is LPT, and this is the HPT. Okay, entropy. So means that a higher value of entropy, if the entropy increase, then the vertical distance means the expansion between the turbine, the expansion process will increase, means the work output will increase. Okay, we look at between the difference between 5 to 6 and 3 to 4, the difference 5 to 6 is higher, right? The change in the temperature is higher. When the change in temperature higher, it means that the expansion, the work output, supposedly the work output is higher for 5 to 6 compared to the work produced 3 to 4, because the change of temperature is higher. The work done, the work produced is higher. Okay, so that's why this phrase, this point means, okay, the vertical distance between any pair of constant pressure line increase as the entropy increase. So if you increase the entropy, the work produced will be increased. Okay, so if you look at here, if we add this reheat cycle, okay, supposedly the sum of this work output, which depends on the temperature, the work output will be higher than the basic cycle. The basic cycle just now from 3 to 4 prime. Okay, the basic cycle just vertical line directly, only one stage of expansion. Okay, so 3 to 4 prime, the work done is less compared to if we add another stage of expansion, another stage of turbine. Okay, so 5 to 6 reheat back. So supposedly the work output, work produced by the turbine increase. Okay, by using this reheat cycle. Okay, so assuming the gas is reheated to a temperature equal to T3. Differentiation of the expression of the specific output shows that the optimum point in the expression at which to reheat is where the pressure ratio for the HP and LP equals. Okay, this is just explanation of what I showed just now. Okay, ada graph tak? Also these are the equation, okay, that we can use the relation between the specific work and the efficiency, cycle efficiency with the with the ratio of the temperature and the pressure ratio. Okay. So with the equation 2.4 and 2.5 here, 2.5, we can again sketch the graphic, this figure 2.5b. So we can see here, okay, we have the dot line, our reference, the simple cycle just now, that is our base reference. We always try to compare it back with the reference as basic cycle. We want to see whether with the modified cycle, whether we improve or not the performance. Okay, so here for efficiency, cycle efficiency, if we use this reheat cycle, okay, if we look at here, by using this reheat cycle, the efficiency drop, okay, compared to simple cycle. Okay, the reheat cycle, the efficiency drop. Okay, means because we reheat, means that we have to burn the fuel and the working fluid air at least twice. We burn it one more time, means that the heat being supplied double. Because we see just now, bila kita guna reheat ni, kita kena burn dia sekali lagi. So bila kita burn dia, of course kita nak heat, kita use more fuel. Combustion process berlaku sekali lagi kan after benda tu. So dia guna more heat, kita perlukan heat lagi lah, more heat supply. So that's why the efficiency reduce. Okay, but okay, the efficiency reduce, the reason lah. However, work output can be increased. Okay, specific work output, figure 2.6 is increased. So that's why I paste back figure 2.2b earlier so that we can compare, we can see the change. If we add this reheat, if we use this reheat cycle, the specific work output or the work produced, the power produced by the gas turbine cycle, reheat cycle can be increased. So we can see here for T equals to 5, the specific work output can reach value around 2. However, with the simple cycle, basic cycle just now, at T equals to 5, the specific work output is only around 1.6. Okay, means that by using this reheat cycle, we can increase the power output, but the efficiency will be lower, decrease. Okay, so that is pro and cons. Another pro and cons. Pro, the benefit is that work output increase, better work output, but less efficient. Okay, less efficient for this heat cycle. Okay, so depends on our objective, our aim. If we want to produce more power, our objective is to produce more power despite whatever the efficiency is of the engine, then maybe we can opt for this reheat cycle. Okay. Okay. Berapa dah? 8. Okay. So this number 4, I think number 4, another cycle is, I think this is the last modified cycle that I have in my slide. Okay. So this number 4 is the cycle with reheat and heat exchange. Means reheat and regenerator. So double lagi. Okay. So what if we modify the gas turbine cycle and add both of these heat exchanger, reheat and heat exchange. Okay. So the TS diagram is that one. Okay, on the right hand side, more complicated. Okay, so we have the regenerated, the heat from the hot side to the cold side, 2 to 7. Okay, to save the fuel, and but at the same time we reheat the working fluid, 4 to 5 again. Okay, so there are 2 extra process. Okay, so cycle with reheat and heat exchange, the higher exhaust gas temperature is now fully utilized in the heat exchanger, and the increase in work output is no longer offset by the increase in heat supply. Okay, so we see just now, if we just use a reheat cycle, kan tadi kan, reheat cycle previously, our work output increase, but however, our efficiency decrease. So that's why this idea, reheat and heat exchange combined came. Okay, so that we can produce a higher work output, work specific work, at the same time still maintain or increase the whole cycle efficiency. One of the reason one of the idea. Okay, the higher exhaust gas temperature, because when we reheat just now, we achieve a higher temperature of the working fluid. So the idea of this combined cycle is that we want to use the higher temperature of the working fluid that is already been reheated. Okay, so we can use it to regenerate. We can regenerate it and use to preheat the cold side of the fluid. Okay. When heat exchanger is employed, the efficiency is higher with reheat than without, as shown by comparison of figure 2.8 and 2.4. The formula constantly less exhibit the temperature. Okay, so this one. Okay, the figure 2.8. Okay. So we can so the problem of the constraint of the lower efficiency with reheat cycle just now can be maybe overcome by adding heat exchanger also to the reheat cycle, so we can maintain or lower the decrease of the efficiency, okay, compared to just reheat cycle. Okay, so those are the three modified cycle and one simple cycle that I introduced in this topic. Okay. So actually, there of course there are a lot more with intercooling, right? What else? Ada lagi banyak lah kan? But here I will only show those 4. Okay. So before I proceed with the second part, okay ke semua? Do you have any question or anything want to comment or to ask?
Doctor, just to comment, I haven't seen this system used on aircraft application, maybe on ground application probably.
Yeah, maybe more on the power plant, right? Because yes, I agree, because one of the constraint for aircraft maybe the weight, right? The impact of the extra weight added to the engine kan. So yeah, maybe that is the constraint lah. Okay, so but we maybe we can but I know that research has been continuously done, okay, to maybe to modify to implement this concept also in aircraft engine. Tapi saya faham lah, I understand that the one of the reason is due to the weight lah. So aircraft engine mungkin jarang kita ada buat modified cycle macam ni kan. Dia lebih banyak kepada gas turbine yang power plant lah konsep. Okay.
Okay.
Okay. So we continue. 10. Okay. So maybe I I don't expect to finish all this subtopic tonight, but we can continue a bit more. Compressor and turbine efficiency. Okay, about the compressor and turbine. Isentropic efficiency and pleiotropic efficiency. Okay. At the end of the session, blah, blah, blah. Okay. Okay, so the assumption that we made just now, the performance of free cycles differ from ideal cycles for the following reasons. Okay, fluid velocities are high and change of kinetic energy cannot be ignored between inlet and outlet compression, and special process are irreversible, adiabatic, and hence increase in entropy. Okay, just now, one of the assumption that we made, one of the 6 assumption that we made is that we assume that there are in ideal cycle there are no kinetic energy done. Okay, it means that we assume that the velocity of the working fluid air, inlet and outlet of each of the component constant or more or less the same. Okay, but in reality, actually there exists somehow some portion of kinetic energy, means the difference of fluid velocity between inlet and outlet. Sometimes it cannot be totally being ignored. Okay, so that's why in reality, the performance of compression, compressor and expander, turbine expansion process are actually irreversible adiabatic. Just now we assume it is reversible adiabatic as entropy, but actually in reality, of course, it is irreversible and has increase in entropy. So when it is not reversible, so there are the entropy, there is increase in entropy. Okay, so there is kinetic energy somehow. Okay, so how are we going to define or characterize this performance? Okay, this change. Okay, friction results in pressure loss in combustion chamber and heat exchanger, and also in inlet and exhaust duct. Okay, another thing, within the heat exchanger or within the combustion chamber, there exists also pressure loss. Okay, due to friction, etc. Okay, so that one also we cannot neglige. If a heat exchanger of an economic size, terminal temperature difference are inevitable. The compressed air cannot be heated to the temperature of the gas leaving the turbine. Okay, so these are all the actual reality happen in the occur in the cycle. Okay, slightly more are required. Okay, to overcome those friction. Okay, the values of the working fluid vary throughout the cycle. Just now we assume Cp, specific heat, and the gamma heat ratio constant, but actually those values are dynamically change with the temperature, right? Due to the internal combustion, chemical composition, etc. Okay. Another reason is that the definition of the cycle efficiency of an ideal cycle is clear, but not for open cycle. Okay, open cycle, which is aero engine, is use an open cycle, the Brighton cycle. Okay, so we know that the those component, compressor, combustion chamber, those has actually pressure loss, inefficiency, right? So we need, okay, other information, other parameters to characterize, to measure this open cycle. One of them is SFC, is what we call specific fuel consumption or thrust specific fuel consumption. Okay. Oh, panjang lah. Ini tak apa. With internal combustion, the mass flow through the turbine might be thought to be greater than through the compressor by virtue of fuel added. Okay. So this is about turbine inlet temperature. Okay. There are some portion, 1 or 2% of the compressed air is bled off for cooling turbine. Okay. And the turbine inlet temperature higher than has a maximum temperature that it can withstand, that it can accept. Okay, so that's why we need sometimes turbine cooling, okay, internally air cool turbine. Okay, so this is okay. Stagnation properties. Okay, just a minute. Saya tengok slide. Okay, tak apa. So we look at this stagnation properties. Saya rasa saya skip tadi yang tu. Okay, stagnation properties. Okay, kinetic energy terms in the steady flow energy equation. Okay, we use also these stagnation properties, or sometimes we call it as total properties, written as HO here. Okay, instead of just simply H enthalpy, we use this HO, H total. So theoretically, it means that a total enthalpy which take into consideration the dynamic movement and also static. Okay. Okay, this one. Okay. This one, the energy equation just now. For example, at the diffuser or at the nozzle, because we know that at the diffuser and nozzle, the kinetic energy cannot be negliged. Okay, it's not negligible at the especially diffuser and nozzle, because there is a high change of velocity c here, high change of kinetic energy, so we cannot neglige those part. Okay, so so for diffuser or nozzle, we have the kinetic energy term. Okay, but for example, this one is a H. Okay, for a diffuser, okay, we have the function is to decelerate, okay, to slow down the air intake is before it enters the compressor. The working fluid is being decelerates. Okay, so with this value, these properties, stagnation properties, we assume that the working fluid intake is undergoes means the velocity is when it is introduced in the diffuser, it will become become to a complete stop. Okay, so that's why at the end, or at the end of the diffuser, we assume that the velocity is nearly zero. So that's why zero here. And thus we can use the definition, and thus H stagnation or H total, H0 is defined by equation 2.6. H stagnation equals to H plus C2 square over 2, the kinetic energy. Okay, so this is like the static enthalpy, and this is like the dynamic. Okay, so this is the kinetic energy part. Okay, so from this stagnation enthalpy, we can rewrite, okay, the equation in terms of temperature, because we know enthalpy is CPT just now. Okay, so we can also write this equation 2.7. So this is stagnation temperature. So stagnation temperature links the stagnation temperature or total temperature is the static temperature plus this is also in Kelvin, in temperature units. Okay, C2 square over 2Cp, the dynamic, or sometimes we call it dynamic temperature. Okay, so these stagnation properties or total values is what usually being measured. Okay, in the cycle. Okay, so in the cycle we measure both of the static and dynamic properties, parameters. Okay, so from So the same thing, okay, for either in the compressor, turbine, etc. The equation, the expression that we have earlier, we can change it into stagnation form. T total, T02 minus T01. Okay, the notation macam tu like that. Okay, TO2, TO1. So actually later on in next few chapters, Dr. Izani we introduce those chapter. We will see the turbofan cycle, turbojet cycle. Okay, so with me right now, I introduce first the gas turbine cycle, Brighton cycle in general. Okay, later on in future next chapter, you will see the some application, okay, of this gas turbine cycle, this shaft power cycle in aero engine, which is turbofan, turbojet, turboprop, etc. Okay, so when we want to evaluate those performance, those cycle performance, generally we will use this stagnation properties, stagnation values, stagnation temperature, stagnation enthalpy instead of the static enthalpy, static temperature. Okay, so sebenarnya macam nanti bila apply kepada engine aero engine lain nanti, sebab ni just basic gas turbine dulu. Okay, nanti bila ada next chapter akan tengoklah cycle-cycle untuk turbofan, turbojet semua tu, dan properties yang kita calculate tu sebenarnya ialah total or stagnation properties. Okay. Similarly for heating process without work transfer, so it's the same for heat transfer, Q, and then we can also write the link the stagnation pressure with the temperature by using the same equation of state for ideal gas just now. Okay, equation 2.8, we can write it this way. So we can link the pressure and temperature. Okay, yang tak ikut. Okay, this one. Okay, the same thing again. Okay, those expression, okay, can be written also between inlet and outlet of each of the component, means exit and exit and inlet input of the component 1 and 2. Okay, for example, diffuser or compressor. Okay, so the total pressure exiting the compressor, the ratio of the pressure is equal to can be linked with the ratio of the temperature, inlet and exit of the compressor or any other component. Okay, so macam ni pun boleh. So ada banyak lah dia punya ni of gas which can be used with static values to determine the combined thermodynamic and mechanical state of the stream. We can also use both at the same time, the stagnation properties with the static properties. Relation pun valid juga. Okay. Okay. So in TS diagram, what will happen in TS diagram? Okay, just now we only see, for example, this is the TS diagram for compression process. Okay, just now we only see from point 1 to point 2.2, right? Ini 1 to 2 just now, okay, static from 1 to 2. Or from 1 to 2 kat sini lah. Ni the ideal process or real case. Real case is a bit this is real case 1 to 2, this around sikit. Kalau the ideal isentropic 1 to 2 prime. Okay, that is only for static states. Okay, now with the knowledge of the stagnation state, so actually there is a slightly difference of temperature location. Okay, for example, at T1, okay, with the static temperature, we have T1 lower than T total 1, 01. For example, if T1 here is 20 degree, but the actual total temperature at location 1, inlet of the compressor, is actually maybe higher, 30, for example, 30 degree. Because the total temperature at the inlet compressor is actually we have to take into consideration this dynamic temperature, which due to the kinetic energy just now, due to the velocity change. Okay, for static state, we neglect the dynamic or the kinetic energy, but actually in actual case there is some different. Okay, so that's why we use, instead of just T1 as a static point, we use T total one when we want to evaluate the cycle. Okay, because there's a slight change due to the kinetic energy. So the same as the point exiting the compressor or exiting the turbine other components, the destination point at the exit also differs. Okay, it's different. Instead of a static just now, 2 prime or 2, but in real it's actually 0 2 or total destination 2 due to this dynamic temperature or dynamic value properties, kinetic energy. Okay, so it does affect, okay, the whole cycle, actually this whole cycle performance when we take into consideration this stagnation properties. Okay. Isotopic efficiency. Okay, sekarang pun isotopic efficiency tadi sikit ada slightly error in the slide. Okay, right now A26. Mana banyak juga. Tak apalah. Maybe 1 or 2 slides more. Okay. Isotopic efficiency. So since turbo machines are essentially adiabatic, the ideal process is isentropic and the efficiency is called an isotropic efficiency. Okay, turbo machine, those are compressor and turbine. Okay. So in ideal process just now, we assume that those components, those turbo machine is isentropic, adiabatic and reversible. So that's why the efficiency of this component, compressor and turbine, sometimes we call it as isentropic efficiency. It's actually the efficiency of the compressor and turbine, the component. Okay, just that the name is called isentropic efficiency due to the process, ideal process tu. Okay, so for example compressor. Okay, compressor, the efficiency of the compressor, the isentropic efficiency of the compressor is written as eta C tu symbol, that symbol, this one. Okay, so we know that the relation just now, in compressor there is no heat transfer, adiabatically, no heat transfer, but there is a work done, work being used. So we only take into consideration the work, the energy, the enthalpy is the work. Okay, CPT. So CP, with constant CP specific heat, so we can eliminate that CP. So we have the efficiency of the compressor. Above is the ideal case. Okay, and below the denominator is the real case. Okay, so the ideal over the reality. Macam ni tadi. Oh, tak apalah. This is now. Okay, so the change of temperature T01 and T02 prime over the T01 and T02. Okay, ini versus ni. Okay, so the difference of this temperature over this the real process. Okay, so that is the efficiency for compressor. actual versus ideal. Actual over ideal. Okay. And for turbine, it is the opposite. Okay. For turbine, because we just have to remember that this the value of efficiency cannot be higher than 1. Okay. So that is the purpose. So if you can just think it that way, so we know which denominator, which one is to put at above, and which one is at the denominator below. Okay, so just so that our efficiency is not higher than 1. So the lower difference of temperature should be at the above. Okay, so these are the expression for compressor and turbine efficiency. Okay, so sometimes the compressor turbine around 0.6 or 0.8 the efficiency. Okay. Okay, we can also write those equation. If we rewrite the equation, we can link the compressor efficiency with the pressure ratio. Okay, pressure ratio of the compressor. So we have this. So sama jugalah. For turbine also the turbine efficiency with the pressure ratio of the turbine, PO3 over PO4. Okay. So ni pun sama. Okay. With PA, P ambient, because usually the P4 outlet of the turbine is at atmospheric ambient pressure. Okay, so that's why we can replace the P4 at the exit of the turbine with PA, ambient pressure. But it's the same relation just now. Ni banyak ni. Okay, last one. Okay, maybe I stop here. So this is the diagram, TS diagram for turbine. Just now for compressor, this is for turbine. So figure 2.10 indicates which the diffuser reduce the final velocity to a negligible value. Okay. Okay, so so if we add, okay, the turbine is fitted with exhaust diffuser, we can reduce the final velocity. Okay, reduce the final velocity of the at the end of the turbine. Okay, so if you reduce the final velocity, so the PO4 here, okay, instead of this location, okay, so okay, so we can reduce it to here, okay, by adding the extra exhaust diffuser. The turbine pressure ratio is seen to be increased from PO3 over PA to PO3 over PX. Okay, this is the A. PO3 over PA. Okay, this is X. Okay, PO3 over PX. Okay, turbine pressure. Okay, so when we increase the turbine pressure ratio, of course we increase the power output, work output, network output of the cycle. So that is one of the interests. Okay, I think I will stop now. You will continue, insyaAllah. Okay, with other topics. Okay, we'll stop at the isentropic efficiency first. Okay, any questions or any comments, feedback before we stop?
Doctor, yes,
Yeah.
just now you mentioned about the diffuser and the stagnation point. Where is there's any specific area where the diffuser is located?
Okay, from here, okay, kinetic of the gas leaving turbine is recovered in an exhaust diffuser. which increase the pressure ratio across the turbine. So the diffuser is fitted after the turbine from here.
Okay, not like outlet of the compressor or something.
Because here the interest is to kind of to reduce the velocity, right? So because the function of diffuser to decrease decelerates a bit. So because exiting at the end of the turbine, supposedly the velocity of the gas is high. So maybe that is one of the interest is that's why this diffuser is fitted, is implement at the turbine instead of at the compressor.
So
Because
when you mentioned the stagnation point just now at the diffuser, are you referring to this diffuser here at this location?
Here or at the beginning just now?
At the beginning just now.
The diffuser before the compressor.
Yes. It's before. I mean the inlet.
Yeah. Yang masa
Okay.
at the beginning when I explained about the stagnation properties.
All right. Okay. No, the reason I asked because there's a convention in aviation maintenance that the diffuser is located outlet of the compressor. So that's why I don't want to confuse myself. So when you talk about diffuser, you mean the diffuser at the inlet?
Yes, generally at the inlet intake and diffuser,
Yeah.
compressor, and the condensation, etc.
Okay.
Usually
All
yang
right.
this one lah.
All right. Okay.
Okay. Okay. Nothing else. I will stop here. Okay. So we will continue inshallah next week with this the same topic again. Inshallah. Okay. Okay. Thank you very much and good night, everyone. Assalamualaikum.
Okay, thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.